The night of May 17, 1943 left a mark across Germany that its engineers would spend years trying to erase. The Royal Air Force's Lancaster bombers had done what many in the Luftwaffe's high command privately believed was impossible: strike the heart of the Ruhr Valley's dams with precision. The Möhne and Eder breaches flooded hundreds of factories, power stations, and railway lines. What startled German scientists wasn't merely the destruction, but the machine that delivered it. Reports from flak batteries describe bombers flying low, steady, and unerringly coordinated, carrying payloads heavier than any German aircraft could manage. Within weeks, orders circulated through the Reich Air Ministry: capture one intact Lancaster, study it, and replicate its performance. The operation was assigned to the Luftverteidigungsanstalt in Braunschweig and the aircraft manufacturer Heinkel, whose engineers had already attempted to build heavy bombers under tight restrictions. They were told to analyze British engineering principles, especially the Lancaster's structural design, fuel efficiency, and payload integration. By July 1943, pieces of downed Lancasters arrived at research depots across occupied Europe. Wreckage from the raids over Hamburg and Kiel provided partial blueprints, and German technicians laid out twisted aluminum frames, control surfaces, and engines across factory floors under harsh white lamps. What they saw unsettled them. The Lancaster's construction was deceptively simple yet brilliantly modular. British engineers had designed its fuselage around uniform frames and standardized fittings, allowing sections to be replaced rapidly under field conditions. The Germans, accustomed to overengineered airframes with bespoke components, couldn't grasp how an aircraft so large could be built so efficiently. When a mostly intact Lancaster from a crash near Rotterdam was recovered, the team finally had a working sample. Its 4 Rolls-Royce Merlin engines were removed and studied at Junkers' propulsion lab in Dessau. The findings embarrassed German designers. Each engine delivered 1,640 horsepower with remarkably consistent tolerances, something their Daimler-Benz counterparts struggled to maintain even on test stands. The British engines also exhibited superior altitude performance, thanks to 2-stage supercharging that German factories couldn't easily reproduce without significant redesign. The Braunschweig engineers quickly realized that building a German Lancaster wasn't merely a matter of copying blueprints. It required adopting a manufacturing philosophy their system didn't support. Still, orders from above were absolute. A project designation was issued: Project 1075. It would attempt to create a 4-engine heavy bomber capable of matching the Avro Lancaster's range and payload. But the first mock-ups revealed the challenge ran deeper than anyone expected. By late autumn 1943, the Heinkel Design Bureau at Rostock had cleared one hangar entirely for the new experiment. Engineers who had spent years designing sleek single-engine fighters now found themselves confronted by a bulky airframe that dwarfed anything in their experience. The goal was clear: replicate the Lancaster's 33-meter wingspan, its internal bomb bay capable of carrying nearly 10 tons, and its ability to stay aloft for 9 hours without refueling. Yet the tools, materials, and even the industrial mindset to achieve it simply didn't exist in Germany's fragmented war economy. Steel shortages forced the use of lightweight alloys that lacked the tensile strength of British duralumin. Skilled metalworkers were increasingly replaced by conscripted labor with minimal training, and precision jigs were shared between multiple factories already overburdened by fighter production. What emerged on paper under the provisional name Heinkel He-177B7 looked plausible, a twin fuselage configuration borrowing ideas from the Lancaster's bomb bay layout, but every subsystem revealed compromise. The engineers confronted their first obstacle with the engines. German High Command demanded the bomber use domestically available Daimler-Benz DB610 power plants, essentially 2 DB605s coupled together. On paper, the combined 2,950 horsepower per nacelle promised better output than the Lancaster's Merlins. In practice, the engines overheated, caught fire, and required such delicate synchronization that test flights often ended prematurely. Pilots reported torque imbalance so severe that simply keeping the aircraft straight demanded constant rudder input. When the test results reached Braunschweig, the verdict was grim. The Lancaster's single-engine reliability made it militarily viable. The German copy would burn itself out before reaching altitude. Attempts to modify cooling systems or redesign the nacelles only made the structure heavier, reducing the bomb load and defeating the project's very purpose. Even the aerodynamics betrayed a philosophical gap between the two nations' approaches to engineering. The British had optimized the Lancaster for stability, not aesthetics. Its thick wing roots and broad tailplane looked inelegant but kept the aircraft controllable even with two engines out. The German prototype, adhering to aerodynamic purity, sacrificed that margin. Test pilot Kurt Scheller described it in his report as an aircraft that wishes to fly fast, but resists flying straight. The Luftwaffe's insistence on speed and altitude advantage clashed fatally with the realities of strategic bombing. Every solution introduced another weakness. Still, the Air Ministry demanded progress, and production of experimental components continued, slowly, uneasily, under growing Allied pressure in the skies above Germany. By early 1944, the Braunschweig facility had turned into a graveyard of half-finished airframes. Metal shavings littered the floor, jigs sat idle, and engineers worked under the distant rumble of American daylight bombing raids. What had begun as a technical study of the Lancaster had devolved into an exercise in bureaucratic survival. No two departments agreed on priorities. The Heinkel Group insisted that without a complete redesign of the power plant, the aircraft would never meet operational standards. Junkers, tasked with producing the engine housings, refused to divert skilled workers from its Ju-88 bomber lines. Meanwhile, the Reich Air Ministry continued to demand monthly progress reports that bore little resemblance to reality. The Lancaster's genius lay in its production simplicity. Thousands of subcontractors in Britain manufactured standardized parts assembled with minimal retooling. Germany's centralized system, crippled by Allied bombing and political interference, could not replicate that model. Every rivet required a permit. Every design change triggered a new round of approvals. When the first prototype finally rolled out for taxi tests in March 1944, it already lagged a year behind schedule. Photographs taken at Heinkel's test field show a vast aircraft with uneven skin panels and temporary plywood coverings where metal was unavailable. Technicians had painted Luftwaffe markings hastily on one side only. The test crew, aware of the risks, approached the machine with visible apprehension. On its second high-speed run, one coupled engine seized, sending a spray of oil across the nacelle. The propeller governor jammed, and flames erupted before the aircraft had even left the ground. The fire crew extinguished it quickly, but the image of the burning prototype circulated through engineering departments like a confession of failure. The British Lancaster, meanwhile, continued to strike with mechanical confidence and quiet precision. Every successful raid over Germany mocked the engineers still trying to understand its structural logic. Desperate to salvage something, German scientists began dismantling their own prototype for analysis. Each bolt compared, each spar measured against what fragments of the Lancaster they still possessed. The deeper they went, the clearer the difference became. The British design emphasized redundancy, multiple hydraulic lines, dual electrical systems, and sectional armor protecting fuel tanks. The German copy cut corners everywhere possible. Weight distribution, center of gravity, vibration harmonics, each revealed an aircraft born of compromise rather than innovation. Yet orders continued: build two more, correct the faults, and prepare for flight testing in June 1944. As Allied troops landed in Normandy, the German engineers still argued over propeller angles. The war had shifted irreversibly, yet the Reich's technical committees clung to the illusion that a new heavy bomber might change its course. At Heinkel's airfield near Vienna, the second prototype, codenamed B7/02, was readied for flight trials. Reinforced oil lines, enlarged radiators, and a slightly reworked undercarriage represented months of effort, but the improvements only masked deeper flaws. During the first climb, one of the coupled engines began vibrating violently. Test pilot Erich Sommer throttled back, but the propeller assembly disintegrated, sending fragments through the wing's leading edge. He managed to bring the aircraft down with minimal damage, yet the report left no doubt. The He-177's twin-coupled system was a dead end. Engineers proposed switching to 4 separate nacelles like the Lancasters, but that required redesigning the entire wing structure. The proposal reached Berlin in July. No decision ever came as fuel shortages worsened and aluminum became scarce. The project was quietly renamed He-277 and classified as a long-term study. In truth, it was already dead. The factories tasked with building its components were under constant attack by American B-17s, the very bombers the Lancaster had helped guide through Europe's night skies. In meetings, senior officers from the Ministry of Aviation of Nazi Germany began to question the purpose of competing with an enemy design that had already mastered what Germany could no longer sustain: large-scale production and consistent reliability. Even Göring, usually prone to grand pronouncements, admitted during one briefing that Germany builds jewels, Britain builds tools. The phrase, intended as an insult, captured the underlying truth of the failure to end the archives at Rostock. A frustrated engineer scrawled a note on one blueprint margin: "We copy what we cannot build." That single line encapsulated the futility of the entire endeavor. The German industrial system, constrained by ideology, complexity, and resource scarcity, could imitate the Lancaster's shape but never its soul, the networked efficiency and pragmatic craftsmanship that allowed British factories to produce one every 2 hours at the height of the war. By the time Allied troops crossed the Rhine, all work on Project 1075 had stopped. What remained were charred airframes, half-melted jigs, and blueprints marked Geheim, filed away in a nation collapsing under its own ambition. When Allied forces entered northern Germany in April 1945, they found the remnants of the so-called German Lancaster project scattered across half-destroyed hangars. At Heinkel's Rostock plant, U.S. technical officers documented 2 incomplete airframes, both riddled with shrapnel and corrosion. One still bore chalk markings from its aborted stress tests, numbers, equations, and the faint outline of a British 4-engine bomber stenciled for comparison. The reports filed under Operation Lusty, the Allied program to recover enemy aviation technology, described the wrecks as educational but impractical. They noted that despite years of effort, Germany had never managed to produce a single reliable 4-engine heavy bomber capable of rivaling the Lancaster. Even the earlier He-177s, deployed briefly against Soviet targets, had earned the cruel nickname Führerzug, the lighter, for their tendency to ignite mid-flight. American and British intelligence teams combed through the surviving documents, fascinated by the scale of the failure. They found memos dated as late as February 1945 still promising imminent breakthroughs. One letter from the Air Ministry's technical office demanded a report on streamlining the bomb bay doors to rival Avro's drag coefficients. The irony was painful. Allied factories by then had produced over 7,000 Lancasters. Germany had built fewer than 50 operational He-177s and none that matched their endurance. The recovered blueprints revealed attempts to mimic British engineering features that had been misunderstood entirely. Wing spars made too thin, undercarriage geometry copied without accounting for differing center of gravity, and electrical systems that failed under combat vibration. When the Allies shipped the surviving components to Farnborough for analysis, RAF engineers studied them with quiet satisfaction. The verdict was not triumphant, but reflective. The Lancaster's strength had never been a secret formula. It was a product of discipline, manufacturing uniformity, and trust between designers and builders. Germany's scientists, bound by political oversight and fear of failure, had operated in isolation, each department guarding its prestige. The result was inevitable. By war's end, Britain's factories stood battered but victorious, their workers having built machines that symbolized collective ingenuity rather than personal glory. In the ashes of the Reich's laboratories, the lesson was unmistakable. The Germans had tried to copy a bomber. What they failed to understand was that they were trying to copy a system. In the post-war years, captured German scientists interviewed by Allied intelligence often returned to the subject of the Lancaster with a mixture of admiration and disbelief. They spoke not of its power, but of its simplicity. Many admitted that when they first examined its blueprints, they assumed the British had hidden design details to mislead them. The rivet spacing looked too coarse, the wiring harnesses too straightforward, the hydraulics almost crude by German standards. Only later did they understand that efficiency was the secret, that the Lancaster's reliability came not from perfection, but from accessibility. Every component could be replaced in hours. Every mechanic could understand its systems. In contrast, the Heinkel teams had chased theoretical brilliance, building complexity into every corner of the aircraft until it collapsed under its own precision. The Luftwaffe's failure to reproduce the Lancaster became a symbol within Allied engineering circles, a cautionary tale studied by design schools for decades. Reports from Operation Surgeon, the British Technical Intelligence Program concluded that German science, when divorced from practicality, yields nothing that can be fielded. That assessment extended beyond aircraft. Jet fighters, rockets, and guided weapons all bore the same mark of technical genius constrained by industrial chaos. By 1946, most of the surviving Heinkel engineers were working under Allied supervision, some assisting with the British Hanley Page Victor project. They studied how Britain had balanced performance with production, learning lessons that would shape post-war aviation across Europe. In the ruins of Rostock, one British officer noted the irony that the same hangar which once housed Germany's failed bomber experiments would soon produce parts for civilian aircraft under Allied control. The contrast could not have been sharper. Britain's wartime factories, designed for destruction, now rebuilt nations. Germany's laboratories, once devoted to imitation, became archives of instruction. The Lancaster had not only survived the war, it had outlived its imitators, its engineers, and even the ideology that sought to surpass it. The attempt to copy it proved something deeper, that innovation is not replication, and that war rewards those who design for endurance rather than vanity. In the end, the German scientists had indeed copied the Lancaster, but what they built instead was a mirror, reflecting the limits of their own empire.